Happy Thursday, everyone. It's 1 p.m. here on the West Coast. This is another episode of the ZEISS Microscopy Micro Minutes. I'm your host for this episode. My name is 𝗦cie𝗰𝗶𝗹𝘀, and I'm an applications engineer at the ZEISS Microscopy Center in Dublin, California. Today, you can see the building back of me. And so today we'll be going through the topic of imaging of non-conductive samples with NanoVP and how that relates to our products directly. I'll go through some slides that explain what the NanoVP is and why you might want to use it, how it differs from other things. One thing to note that there is a place, if you're watching this, that you can have a Q&A and interact with us, and we'll try to answer questions as we go along or at the end. And I'll check that as we go through here. Also, to note that there's a upcoming springtime microscopy will be next week. So that one will be a good one. That'll be another electron microscopy topic on that. So I'm going to go ahead and move on to here. So go through some of the slides first. So we'll start with a slide of, this one just shows the differences between high vacuum normal VP, which means that we've let some gas into the chamber, but not an extra lot. It runs up to about 60 pascals, sometimes less than that. NanoVP has what we call a beam sleeve that comes in, and it makes it where then they have pressure limiting aperture. That then allows you to go higher and with gas pressure if you need to neutralize some of the charging that you would get on non-conductive samples normally than high vacuum mode. And then I'm not going to talk about it today, but there's XPP as well that is related to that. You can go quite a bit higher. And it's a one button click to go between those modes on our microscopes. Okay, so this is just a slide showing that if you have it in normal variable pressure mode, you have gas and the beam is interacting with that gas even before it hits the sample, and it's spreading out because of that. And then you have basically what they call beam skirting, which makes it look like it is not quite as good a resolution and things are a little bit fuzzier than they would be normally. But the benefit of it normally is that you get rid of your charging. So if you don't have NanoVP, this is what you'd use instead. And it's if you do have NanoVP, then it puts in a beam sleeve here, and it limits the amount of gas, the path length between the actual aperture and the gas that's between the sample. So it gives a smaller beam spot size. It gets rid of that, what we call beam skirting, and higher beam current interacts. It improves the signal level and the signal to noise. So that's one of the main benefits, as well as being able to use your in-lens detectors that are up in the column. So you can do that as well. I'm going to go ahead and at this point, I'm going to switch back to going to the video here that I've recorded different segments. I'm on the Gemini SEM 560 for all this. I'm going to start initially with high vacuum 1.2 kV. 109 picoamp. Let's give it a moment here. Okay, so we're on the tool. I've got the SE2 detector selected, which will show the topographical information about the surface of the sample. And right now we're looking at carbon fibers that are been fractured. You can kind of split them so you can see the ends of them. On our interface, we have the macro bar at the top, as we normally have. It's very customized and allows rapid selection of different controls and things instead of having to go to other menus. But let's take a look and see what we have here. And go ahead and do a slow scan. And as I go slower here, you see that we get nice imaging. This SE2, which is a chamber-mounted ever-thermally detector, does quite well. We're at 1.2 kV. It's not seeing a whole lot of charging, which is expected for SE2. The difference, it would be once we go to in-lens, but we'll go ahead and increase the mag at this point. Let's go ahead and go to 2000 mag and move over to something a little more interesting. It has the ends of these little fibers that we see that are broken. We're going to be imaging those. So they're sticking out in free space. They're non-conductive, and so they don't have a lot of path to get any electrons that are building up on the sample off of them. So right now we're at low enough magnification. We're really not seeing an extra lot of charging, if any, which is nice, but we will definitely see that as we go up higher in magnification. So I'm switching now to 10,000 meg. I see just one of these fibers here. Do a slow scan of that, get a little better image. We're still not seeing a lot of charging effects or anything, so it's still pretty nice given the fact we're in high vacuum mode. Next, I'm going to go ahead and switch the detector to the in lens, and we'll see immediately. Okay, so the streaks here are due to it charging. So it's charging, discharging, and it's causing all this streakiness, which we really don't like as part of our image. So it does provide surface information of the fractured carbon fibers, which we would like to have in addition to our topographical information that we were getting. So the typical way of doing this would be to go into the high vacuum and do a very fast scan speed to try to minimize the amount of charging, and then to do drift corrected frame averaging so that it sums up the quite a few, in this case 50 different, let's go back here. It was on 50 different frames, and then the signal to noise is greatly improved when you do that. So that's a standard way of doing things if you're in, you don't have any recourse, you're stuck in high vacuum mode. Let's let that play out. See, the image is decent, but it still has some charging effects. And this, if I go into split mode and do the same thing, do a frame integration, you can see where left-hand side has minimal amount of charging with the SE2, and the right-hand side you see a lot of charging with the in-lens. So what we could do is we can go down to a lower voltage, potentially find a charge balance point or reduce the amount of current and things of that sort. But for now, just taking some additional images here just to show that when we go higher in meg still, so we go to about 25,000 meg, that we still get good images with this SE2. So it doesn't seem to be much of a problem for the SE2. It's mostly a problem for the in-lens detector itself. Oh, it's a pretty nice image there with nice topography. See the little breaks and cracks and crevices of everything that's on the surface there. And if we did the same thing with the in-lens, we're seeing all this streakiness. So that's the whole point of trying to get past that. So we'll go through that. And even with a really fast scan speed of 1, that's not getting rid of that charging very effectively. I'm going to go ahead and skip the 50,000 meg here. Skip through that, and we see the same charging. So as I mentioned before, we can reduce the voltage. So I'll go down to 200 volts, 100 picoamps here. This is on any of this can be done on our Gemini SEM series. Then I'll show with this plus the NanoVP. This one just happens to be the Gemini SEM 560 that I'm using today, and it excels at going down at very low voltages like we're at right now at 200 volts. I'm just getting it set up here on the surface. So we're in lens. We see that there's far less streakiness here, so we're not charging nearly as much as we were at 1.2 volts. We have about the same current. It could have dropped the current potentially if I wanted to, but that wasn't the point of me trying to do this. It's just showing that even when we're down at a very low voltage, we're still encountering some charging effects that are streaking and things like that are not ideal for what we want. And we'd like to completely get rid of them if possible. So do the same thing here, and in lens, taking the drift corrected frame average. So for the most part, you always see the streakiness at the very top, it seems like, and then a lot of this in here is actually doing quite well. It's going to be more of a problem with the higher megs you go. That also causes the sample to drift, so that's why the drift composition frame average is very, very useful for that. All right, so now for the main event. We'll go into NanoVP mode. On the console and the user interface, you just click a button. It changes it to NanoVP mode. It inserts the beam sleeve. And I changed it to, I thought we'd give it a try, this really ramp it up to 15 kV. And we got 250 picoamps. We got a lot more voltage, a lot more current. This would not have been possible to do at all at the high vacuum. It would have been charging way too much. So right now I have the C2D detector, which is essentially the same as the chamber-mounted one that we've been using for the high vacuum, except it's a different detector that works in variable pressure mode. Gives you topographical information, the same as the ever-only one. And the source scan is needed. So there's the NanoVP button that I had pressed. I just wanted to show that. Anyway, the source scans that I'm doing right now are necessary because the gas is actually what's going to give it the signal. So the slower you scan, the better the signal for the C2D detector. If I switch, it also, on the beam sleeve, we have a variable pressure BSD detector that'll show compositional information. We can see there's a speck at the top here that is different in composition than the rest of it. So there's something there. The rest of it's all carbon, which is what's expected. But we can see where this compositional information. Let's go ahead and bump it up a little bit higher in the magnification. And it will slow down the scan. We could take a VPBSD image. I don't see a lot of differences in the composition, but we can definitely see that it's a really nice image. We're getting nice imaging at 15 kV with these detectors that are available. So the one that I haven't used yet is the InLens, and the InLens is the one that is really beneficial as well, in addition to these two detectors, for looking at surface sensitive information. So let me get to that in a moment here. We'll change it to InLens. I need to bring up the bias or biasing the beam sleeve. That is the cone that's on the, and now we see an InLens image. Got to do the same thing as we did before on any charging sample that you would do a fast scan speed, and it will do a drift compensated frame averaging. Maybe we'd take 75 different frames here, had the scan speed of 2, and it looks pretty good. I mean, you don't really see the streaking that you saw in the imaging at the high vacuum mode. So I think we're good to go there. And let's go ahead and increase the magnification here in a moment. Once this is done here, there we go. Increasing to 8kx was about where I could see at the end of this thing here. Right now I'm back in the VPBSD mode, so it gives me some sense of, because the backscatters are not going to be sensitive to charging, so I kind of look at that first, get an idea of what we're looking at. And we'll switch it over again to the InLens and bring up our bias here, and there's our InLens image. We see really nice surface information. It's very surface topography and other things that we can see that are really nice. Probably pretty nice here. So it's looking nice. So that's a good complementary information to the C2D and the BSD images that we get. So I'm going to go ahead and increase the mag again in a moment here. Let's first go back to our pixel average and increase a little more, about 15kx. That way I can see this flake, this bright flake or whatever it is that's on there. That's seems like it looks like a good thing to image. It might charge normally if we were in high vacuum mode. But I don't see any evidence of that right now. So the good thing is we've gotten rid of our charging. Things are looking good. We're able to use our InLens detector in addition to our chamber-mounted detectors. Things are looking nice. You can see quite a bit of the structure down in these areas, and in a moment I'll zoom in. You see all really nice contrast and even some contrast among that area there that we were looking at on that flake. All right, so let's proceed to a little higher mag here in a moment. And move over to some of these ridges and cracks and crevices and image these things. So this would not at all be possible, especially at this kV in high vacuum mode. And you wouldn't get nearly as much resolution in the regular variable pressure mode either. So the NanoVP really gives really good surface information that you're seeing here in these images. There's been many samples that I've had to use this on, and it's amazing that this does what it does. And so it's a really nice thing to have on your system, especially if you're using non-conductive, lots of non-conductive samples. Let's move over to a different area here. That's the same magnification as 25kx. And again, we see really good details here and texturing. We're not seeing flagging. We're not seeing charging. The bright contrast that we see is because it's facing a particular orientation, I think, more so than the other. All right, let's go a little higher mag still, show that we're at 50,000 mag. So pixel size is around 2 nanometers, and the field width is around 2.2 microns in size. So we're at a high resolution range. Let's go ahead and do a drift comp frame integration, and we're pulling out some of this nice texture and things of that we can see. So if we had information that we needed to look at down in these cracks and crevices, we can certainly do that and see that. We'll do one more of these in a moment. And this guy over here, same magnification, just do another drift corrected frame average image here. And again, you can see like the back wall and all these different shapes and things that you can see really nicely in the NanoVP at 15 kV. All right, so now that we've seen that and see it in action, we're going to go and we'll go back to here. So these are images that we've acquired. These are the original ones at high vacuum were at 1.2 kV, and the SE2, as we mentioned, that it does really well. It doesn't charge. Then you get to the inlands and you say, wow, yeah, it's charging pretty badly. These are not images that I could show my colleagues or publish, and would not want to publish these because they don't really look that nice. And it's all due to the fact that it's charging and it's a non-conductive sample. Lower it down to 700 volts, it's a little better. Lower it down to 200 volts, it's even better still. So right around 200 volts, we're getting pretty good. We still have maybe a little bit of charging and things, but it's really difficult to use at 200 volts, and it'll be a lot better if we could just use it at higher kV like we were doing. So we switch it into VP. So this is just, I didn't show you the standard variable pressure mode today, but at the top, it shows some images that are with the C2D, and then on the right side, the right two images or the backscatter. So you do get a little more, you get less of the beam skirting. It gets rid of that, and you get a little more definition on the NanoVP and those modes. And then these are a little bit higher. They're about 5,000 meg images that show the bottom right image has a little crisper resolution just because of the fact that we got rid of the beam skirting. And in the NanoVP mode, these are the ones that in the images that I took as we went along today, they were at 15 kV. These are inlands and the backscatter. So the inlands is on the left and backscatter is on the right. Again, inlands is on the left, backscatter on the right there. And these are the higher mag images here that we had field of views in the neighborhood of around 4.5 microns. And then this was down around 2.3 micron field of view. So it's very easy to use, very easy to just a single button push puts it into a NanoVP mode, and you're ready to go, and you're able to image any of these samples that might not be able to image in high vacuum mode. So the NanoVP is pretty awesome with respect to that. these are just some additional images, I think. And oh, one thing I should mention, I didn't show today, but it's a very big benefit of the NanoVP mode. The beam skirting, as we mentioned, is it can degrade the resolution, but it also degrades the EDS. And this just shows that we have a signal here that's not supposed to be here. This one for the niobium is not supposed to be there. It picks it up because of the beam skirt effect. If you put in the NanoVP, you get rid of that line completely. It's down at 0, and you only see the 10 and things that you need to see. So it's very beneficial for doing EDS as well. So both imaging and EDS benefit from the NanoVP, especially on imaging of non-conductive samples. I'm going to come back now. So that was it. Hopefully you learned some things that you would see that you didn't know about the NanoVP. There's some links and resources here. There's upcoming ZMCC workshops. I'll go ahead and move myself out of the way a little bit. Move me down here. There we go. And there's ZEISS portal, which has a lot of information about our products, or if you need help, if you have a ZEISS tool, you can go to and get information from the portal there. Upcoming live streams that are, including the micro minutes, which are every Thursday at 1 p.m. Pacific time. There's a list of them there as well. And with that, I'll go ahead and take questions if there's any questions. Let me go ahead and see if we have any. All right, I don't see any questions in the chat. I'll just hang out for another minute here. Otherwise, thank you for your attention. And if you have any questions, you can shoot us an email, contact us. If you have any questions about the NanoVP on any of our Gemini SEM tools.